Hello, everybody. My name is Fraser Shilling, Director of the Road Ecology Center at the University of California at Davis. And today, as part of this special session on animal detection systems, I'm going to talk about camera and video systems supported by artificial intelligence as a ways to detect and classify animals of interest. I'd like to start off by acknowledging a lot of partners who helped this project along: the Federal Highways Administration, Deirdre Remley, Mike Ruth, and Dan Buford especially, and they helped get the artificial intelligence part of this still imagery animal classification part of the project off the ground, along with Kristen John and David Waitchen at the Bird Ecology Center, and at Arizona Fish and Game Department, Jeff Gagnon and Haley Nelson, who provided a lot of images to help train different models that I'll be talking about. The CCTV component of the project has been over the last year and a half, and at Nevada Department of Transportation, Nova Simpson has been really the inspiration behind this and has got it off the ground for all of us. I hope a lot of us who are talking at this session today. And the University of Nevada, Reno, Hao Zhu, who is a great intellectual partner and is working on the LiDAR component of some of our work that I'll be talking about. And finally, Vedant Srinivas, who, along with his family, really, but mostly him, have supported the CCTV AI work, which I'll be talking about. So the overview of the work I'm going to be talking about are in two parts. The still image cameras, which are the familiar kinds of camera traps we use to monitor wildlife in ecological monitoring. We want these systems to be reliable and accurate and sensitive. And so when we're associating AI or artificial intelligence with these tools, we also want those tools to be accurate. We're a little more flexible on speed, processing speed. How long does it take to give you accurate classifications of animals in imagery? And sometimes we're a little flexible on false negatives and false positives, as long as our accuracy is fairly high. In the case of the Road Ecology Center, we make these tools available through an open web system so anybody can use them. For video and CCTV work, we are interested quite often in animal behavior, so the moving part of the imagery of what is important. And in the case of driver safety systems or driver warning systems, we want to know what kind of animal it is and where's it going, so we can improve driver safety and animal safety associated with roadways. The requirements are very similar as with still imagery, but now we want speed, processing speed, to be very fast. So we're less flexible about things like processing speed. We're also a little less flexible on accuracy. The approach that we use is built into this overall workflow, which is shown in this diagram and is reflected in another talk at ICOET. Look at Abstract 7 in Multimedia Session 1 by Dave Waitchen to see more information. Increasingly, the steps in this workflow, and this workflow shows going from the camera in the field to the data in the database, and in between, there's a lot of steps usually. And increasingly, those steps can be automated and are being automated. The one surrounded by the purple box, identification of species, is one that we're talking about automating now, and there's other talks in this conference and in other conferences about how we can do that. So with still imagery, this is something we developed back about 3 years ago, an approach using Microsoft Megadetector to first say, is there an animal in an image? And this is really important for getting rid of all of those false positives where you have moving vegetation and other causes of an image being taken by the camera. This tool also allows you to put a bounding box, which is shown in this diagram here, around the animals so that you can count them automatically. With this tool and other tools, you can say what kind of animal it is in terms of a big group of animals. And with certain custom-made tools, you can also identify species, as long as you're able to train those tools with images of that species. Sensitivity and accuracy with these systems decreases with distance to the subject, the animal, and also the size of the animal, whether big animal or small animal, changes your functional distances and sensitivity for using these tools. This diagram shows the workflow for one of our tools, Image ID, and this is based around both conventional image processing tools so that you can isolate and highlight the animal and change contrast and many steps like that. And it also includes an artificial intelligence tool to say whether or not an animal is present, and what kind of an animal it is potentially. There's an example of use of this tool by somebody else, not us, by Jeffrey Hunter in session 21, which is actually going on right now. So you can't see it right now, but you can see the pre-recording in the program. We also built a custom single species tool, and for this we use mule deer because they're a common animal of interest in the West for, to some degree, ecological reasons, but primarily because collisions with mule deer can cause a lot of damage and does cause a lot of damage throughout the West. We use a Curious API in Google TensorFlow to build a convolutional neural network. We trained it with over 50,000 images from 3 different states of mule deer. And that allows us to build a potentially accurate tool. And of course, we test it and we find out if it is accurate. So accuracy is a key component of this process. And these graphs show 3 different tools that we looked at. One is the Microsoft Mega Detector, which I talked about. Second is MLWIC, which is a tool from the literature which we tested. And also the Mule Deer ID tool, which we looked at as well. And so these charts basically show different ways of assessing speed and accuracy. On the bottom left, the y-axis is processing time, the x-axis on the left-hand graph is pixel count, and the right-hand graph is substrate complexity. So as you increase the size of an image or its complexity, you have some effect on Microsoft Mega Detector, which is the top curve, its speed in processing. So it slows down a little bit. The other 2 tools are very fast, and so on this graph, you can't really see very easily, but they also slow down as well. They take a little bit longer to process images that are more complex, sort of larger size, file size. On the right-hand side are charts related to accuracy. And accuracy for all of these is basically on the y-axis. And on the x-axis, you have pixel count, which is the size of the image, and substrate complexity, which is how complex is your background or your foreground or anything that's going on in the picture. And the take-home message from these somewhat complicated graphs is that MLWIC is generally very accurate in terms of classifying whether or not an animal is present, 99, 98% accurate. Our mule deer identification tool does get slightly less accurate with larger file sizes or more complex backgrounds, but probably not significantly. The steep downward trending lines on the bottom 2 charts, that's MLWIC, and that shows that as your picture becomes larger or your background more complex, that tool basically fails to classify animals correctly. So for the Mule Deer ID tool, we developed 2 different approaches. One, using this giant data set of images to train the model, and that's in the top right. And the testing curve is the orange line, the training curve is the blue line. And as you do more cycles of training, you get more accuracy. That's why those curves go up. And basically, we get to around 94% accuracy for this tool. The approach on the bottom right was a different kind of approach altogether. And we got greater accuracy using only 200 images to train. Now, this was a great breakthrough because sometimes you don't have 50,000 images of something. And so you really want to have something that's trainable on a much smaller data set. So that worked out very well. And it really opened the door to more single species artificial intelligence tools that we can deploy with these cameras. With CCTV, we're looking at moving animals. In our case study is wild horses in Nevada near USA Parkway, Nevada 439. And this is working with Nevada DOT. And we were comparing the CCTV, or we are comparing, with LiDAR, thermal sensors, and radar to do a multi-sensor comparison in this live environment. All of these sensors are positioned on a monitoring station, which is self-powered. So we have the ability to develop a self-powering station with one or more sensors if we were to look a few years down the road, both wind and solar. This whole video on the bottom right, you can see horses crossing the road and a truck coming up behind. In this image, fortunately, nobody gets hurt. No animals are killed or anything, so that's great. We call our system EQUIS for Equine Warning and Identification System. We use a conventional CCTV camera and a software called YOLO. And we trained with many images. You can see the numbers there, including images of horses from this area. For more information on this system, you can go to Abstract 191 in Multimedia Session 1. So as tested, when we were testing the system, we had got to about 92% accuracy for horses up to 100 meters away, which is pretty far. Our deployed distance here is actually much further, 260 meters. And so our accuracy in classification as horse went down, but we were able to classify the animal as, the horses as large animals at least, and they weren't misclassified as vehicles or people or anything else. So the system, even though it had trouble accurately classifying the horse as horse versus some other large mammal, it was able to detect and classify it as something important very quickly. It took 0.17 seconds per detection on average, which is pretty fast. So this means we had a very fast, very accurate tool for detecting large animals in the roadside or on the roadway. We did have some issues with tilted animals. You can see the horses coming down on the left. We didn't think to train the system on animals at an angle, so we'll have to work on that. And we're also going to use parts of animals to do the training as well, not pieces from an image. Sorry. So a station like this with sensors, one or more sensors, self-powered and communicating with the world and driver warning systems would allow you to set up a network. And this is shown with these two different stations at different distances. You could have different sensors. They could be netted down a roadway and able to detect and classify animals and decide whether or not to warn a driver warning system about that, and also share the data for constant updating, training, and reporting of the system. So that's the trajectory we're taking. So in conclusion, we have the functional parts for fully automated still camera or CCTV systems, from the point of detection and first image to database or warning or decision-making. All of those parts are present. So we have these now fully automated ecological monitoring or driver warning systems. This reduces the need for manual effort from skilled scientists and means their effort can be spent elsewhere, and also increases the density or the number of cameras we can put out onto the landscape because we're reducing our manual effort. Our deployment is complete, but our testing and retraining and iterating on the system, the CCTV AI system, is still ongoing in partnership with others, especially University of Nevada, Reno. And we're also looking at deploying the system in Washington in partnership with Washington State DOT for different kinds of species detection and different uses, whether it's driver warning or automated ecological monitoring. For more information about this talk, other things the Road Ecology Center does, you can contact me, or you can go to our website. And I really appreciate your time, and we'll take any questions, welcome to take any questions that you might have now or later.